Bom dias. My last lecture will be on a different topic, yet closely connected to classical problems of differential equations. The title will be All About Singular Points in the Plane. I do not include in the title the assumption that the vector fields considered are analytic. If they are infinitely smooth, then sort of a mess is possible, and this infinitely smooth case is not considered. We are only dealing with analytic vector fields. We deal with the isolated singular points of these vector fields. They are isolated even in the complex domain. So, first of all, what students know? In the general course of differential equations, it is communicated that if you consider a vector field in the plane with a zero singular point and higher order terms replaced by dots, and the determinant of A is different from 0, then a singular point. In the linear case, it is a saddle node, focus, or center. The same in the analytic case. If you have the linear part with the face portrait set of the type saddle node or focus, then the nonlinear vector field has a singular point of the same kind. If you have the linear part of the type center, then nonlinear terms may perturb, may destroy the center, but they may preserve it. If they destroy the face portrait, the singular point becomes of the type focus. So this is what is communicated to the students. But what if determinant of A equals 0? The singular point may be very much complicated. And for the description, even for the description of the answer, Arnold and Tom in 70s suggested a concept of algebraically solvable local problems of analysis. So we are now on one hand, you are in a very general context. You consider a local problem given by some analytic tools. And the first problem is determine the face portrait of an analytic vector field at a singular point in the plane. Another problem is describe a singular point of a critical point of the function. Level curves of a describe level curves of a function in a neighborhood of a critical point. This is subject of singularity theory, and I will say nothing about that. We will think only about vector fields in the plane. And the local problem is like this. Is the vector field Lyapunov stable or not? So let us keep this question as a model. There are other questions. For instance, can we plot the face portrait up to a homeomorphism? Or does the face portrait considered up to a homeomorphism similar to a prescribed one? So local problems of analysis. According to Arnold and Tom. From the naive point of view, we want to do the following. In the student's case, knowledge of linear terms and linear terms of this type is sufficient to plot the face portrait of the singular point. In the general approach, naively, we are doing in the following way. We decompose the vector field in the Taylor series, and we take Taylor polynomials. Linear part is a Taylor polynomial of degree 1. If it is insufficient, let us take a Taylor polynomial of degree 2 and try to determine the face portrait. Or we deal with the question, with a binary question, the answers are yes or no. For instance, is the singular point Lyapunov stable? So let us keep this question in mind. There is a question with the answer yes or no, no here everywhere, maybe yes, maybe no, maybe yes, maybe no. And if the linear part is a center, there is a question. We do not know the answer. So we, if the linear part is insufficient, we take the second degree 2 Taylor polynomial. If it is insufficient, we take degree 3 Taylor polynomial, and so on. In a more scientific way, this should be translated in the language of jets. A jet of a vector field at the point 0 and of the order n is the set of all the vector fields W such that they differ from V by something that is smaller than r to the n. R is the magnitude of the radius vector, the polar radius. So this is the jet. And we have a question. With the answers yes and no. So, with respect to this question, a jet of a vector field is positive if the following holds. The jet is a class of vector fields. Any vector field in this class is a representative. So the jet is positive if the answer is yes for all the representatives of this class, and negative if the answer is no for all the representatives of this class. For instance, when you have a linear saddle, all the representatives have this linear part, and no matter what nonlinear terms. And the stability question has the negative answer for all the representatives of this class. So it is positive if the answer is yes for all representatives, it is negative if the answer is no for all representatives. And it is neutral. It may be symbolized just as a question sign if yes for some representatives and no for other. Now, the local problem is algebraically solvable if the sets, I forgot to give you the notation for positive, the set of all positive jets is denoted by Gn0. So jets, class of jets at 0 of order n with the positive answer. Negative neutral we can put here the question sign. And this is the collection of set star. R suppose that as a model that the jet space is one-dimensional. It is absurd, but it is spectacular. The picture may be like this. In general, the picture is like this. It may be more complicated, but schematically it is like this. So I want to attach algebraicity to this splitting. This is x greater than 0, x equals 0, x smaller than 0. And the sets are semi-algebraic. That is given by a finite number of algebraic equations and inequalities. Like here. But here we have a very simple polynomial. Here the polynomials are more complicated. So probably there is a vector polynomial, and all the components are greater than 0. This is something like this. And this is something like this. All these are semi-algebraic sets. And the problem is analytically solvable, provided that the functions PQR are not polynomials but analytic functions. And all these are the functions in the jet space. So if you fix coordinates, then the n jet is given by the Taylor polynomial of degree n, and then the function or the polynomial or the analytic function depends on a finite number of Taylor coefficients. So algebraically or analytically solvable. So examples. Once again, we start with the linear part, and it corresponds to purely imaginary but non-zero eigenvalues. Then the distinction between center and the focus, or better to say, the understanding whether the point is Lyapunov stable or not, this problem is algebraically solvable. And this was known to Poincaré and Lyapunov. Exists the Poincaré map, delta, say, you take the point, a cross section, R a parameter here, real one-dimensional, and you are interested in the Poincaré map. And the Poincaré map has the form I should better put R here. And this is the sum. So the Poincaré map is an analytic function in R. It is decomposed in the Taylor series in the degrees of R, and the coefficients may be expressed as polynomials. So-called Lyapunov focus values, and the nth polynomial depends only on the n jet of the vector field V. So this is a polynomial of a finite number of variables. And let me briefly denote this as Ln of V, but we remember that V is an infinite dimensional argument, and Ln depends only on a finite number of variables. So suppose that we have equals 0 and non-equal to Ln plus 1. And this Ln plus 1 is greater than 0, then the point is unstable. And if it is smaller than 0, then the point is Lyapunov stable. So this problem is algebraically, the solvability problem for such vector fields is algebraically solvable. The set of the nth set of neutral jets is given by this algebraic equation, and in the set of n plus 1 jets, you have the domain where this inequality works, unstable jets, and this inequality holds stable jets. And neutral jets in the space of n plus 1 jets will be given by the system of equations, this one plus this equation equals 0. I did not finish yet the definition. For all n, yes, for all n. The last part of the definition is the following. The codimension of the set of neutral jets tends to infinity as n tends to infinity. So, as you increase n, the neutral set becomes more and more negligible. In a sense, there are jets for which you cannot solve your question. Suppose that you have taken a vector field with an actual center. Then all the Lyapunov focus values will be 0 for this vector field. But you live in a world of finite order jets. So you see that your 100 order jet does not give you an answer. Then 1000 order jet also does not give you an answer. This will be in case of the center. But you will never stop. You will be in a finite time, you will be never sure that all the jets of your vector field of all orders are neutral. But this is codimension infinity. So for a great majority of jets, you have the answer. So this is this is the definition of the algebraic or analytic solvability. Let me communicate you the general results that I want to explain you more or less in details. The situation is the following. Main results. First, the stability problems traditionally it is called the center focus problem, distinguishing of center and focus. The stability problem, center focus problem, is not algebraically solvable. B. I will write now some phrase with terms which I will immediately explain after. Distinguishing characteristic and monodromic fixed points is an algebraically solvable problem. Characteristic fixed points are the fixed points with some trajectory entering the singular point under a certain direction. The other part of the phase portrait is not mentioned. If you have one orbit like that, then your point is characteristic. A monodromic fixed point is a point, I again plot the cross section, for which a Poincaré map is well defined. The orbit may be complicated, but it will return to the same ray. And this is the monodromy map delta. And a theorem is that a singular point theorem, rather elementary theorem. A singular point of an analytic vector field is either characteristic or monodromic. It is not a difficult theorem. Let me now continue my list. Description of the topology of a face portrait of the vector field near the characteristic singular point is an algebraically solvable problem. It is a result of efforts of many mathematics during the whole 20th century. I will give only some short comments on it. And D, the center focus problem for monodromic fixed points, is analytically unsolvable. In sense of classical definition, in sense of the classical definition, and analytically solvable in sense of slightly changed definition. the statements A, B, C are the fruit of efforts of many mathematicians during the 20th century. It is now quite popular. It is included in the textbooks, for instance, in the remarkable book of Dumortier, Libre and Artes on the qualitative theory of differential equations. So ABC is classical. What about D? In the classical book, authors stop before this problem and say that it is open. The solution of this problem is the result of the lifetime effort of my student, unfortunately my late student, Natalia Medvedeva. In the last part of the lecture, I will try to give you hints, not a detailed description of why C and probably D, I'm not sure that I will have enough time for D, why all this holds. I will give an example for C. I will go in the very same steps as Laura have gone in the last lecture. Here are higher order terms. Here are higher order terms, and here are the homogeneous polynomials. Probably it's better to make Q large. The homogeneous polynomials of degree n in x and y. The first ones that do not vanish. We combine a polynomial Rn plus 1, which is yqn minus xp, xqn minus ypn, and we take u equal to y over x, and this means that the neighborhood of x is lifted, this is the xy plane, to the Möbius band. Every line is lifted to the line with the height equal to its tangent, to the tangent of its polar angle, to the tan of its polar angle. So we glue in a projective line instead of the singular point. And it is convenient to plot the picture in a slightly different way. We replace the disk with the interior part of a circle. And we write down now the equation in terms of x dot. It was as before, but we replace y by ux. And y dot equal to a fraction x to something multiplied by r of 1u plus x to something. So if r of 1u is different from identical 0, then x cannot be cancelled, and the line x equals 0 is invariant. The singular points here are x equal to 0. They are all on this line, and they are roots of r. So I will give you a picture what may happen. I give you, and I neglect what is plotted inside the circle. They are two saddles and two nodes. And this is the picture in the polar coordinates. We can turn back to the original plane, just squeezing this circle to a point, and an orbit that entered the point on a circle with some angular coordinate just enters 0 with the direction of this polar, given by this polar angle. So we have two trajectories coming like this. All these trajectories do not touch this circle and come away from the neighborhood. These trajectories will be also like this, but all these trajectories will will enter the neighborhood of 0 and never quit it. This comes from this sector and this comes from this sector. And what is interesting, there will be trajectories that quit 0 in one direction and return in the other. And these are so-called hyperbolic, parabolic, and elliptic sectors. Elliptic is this one. Parabolic are these two, and hyperbolic is this one. So this is an example of a picture what may happen in a neighborhood of a singular point. And solution of the problem C may be summarized as a theorem. A neighborhood of a characteristic singular point of an analytic vector field is split into a finite number of sectors, hyperbolic, elliptic, and parabolic. And this is the complete description of the positive phase portrait near a singular point, though, as I said, it is a very heavy job to justify this. So, a neighborhood of a characteristic singular point I do not write of an analytic vector field because from the very beginning we are dealing with the analytic vector fields only. Is split into a finite number of elliptic, parabolic, and hyperbolic sectors. And the way, I do not like to write the proof, the way to this answer is successive blow-ups. So here is one blow-up. The blow-up is here in the title, and this is the blow-up. It may happen that after one blow-up, you already have a clear picture of the phase portrait near the pasted-in circle. If not, you have questionable singular points, and you make a blow-up once again. And the desingularization theorem that I even do not formulate here for the lack of time says that after a finite number of blow-ups, you will have a definite answer about the topology of the phase portrait. Nobody formulates this theorem like this. The conclusion is more detailed, but I will not give you these details because I want to concentrate myself on D. And here, in the case D, another blow-up procedure is suggested. It is a blow-up using the Newton diagram. And I will only describe to you the Newton diagram, and the blow-up process will be not delivered in details. I will just give a hint to this process. So we have now not the usual system. Usual system is to write x dot equal like this, and for sure we begin with the Taylor decomposition of the first component of the vector field like this. But it is more convenient for our goals to multiply x dot by y, to multiply all the previous series by y, and to write the result like this. And x y dot equals to y and all this is V, the vector field V. By definition, we will now plot the picture inside the integer lattice on the plane ij. So if we have a point with integer coefficient coordinates ij, we just write it like this. So the support of V, it is just a subset of this lattice, is the set of all ij such that the vector aij, bij is different from 0. So at least one component is different from 0. For instance, if you have the homogeneous part here of degree n, then the lower order terms will be located here on the line I plus j equal to n. But in general, the situation is more complicated, and the support is something like this. Now you take the convex hull, or better to say, we take the convex hull, yes, of the set for any point in the support. You attach a positive quadrant. You take the union of these quadrants, and then you take a convex hull. There is an angle not equal to pi. And the boundary of this convex hull contains two rays, and a broken line with finite number of edges. And this broken line is called the Newton diagram of V. And instead of simple blow up defined above, there is a more complicated blow up process related to the Newton diagram. And there is a notion of degenerate or non-degenerate Newton diagram. It is similar to the non-degeneracy condition here. Non-degeneracy condition in the problem C is the polynomial R of 1U has simple roots, no multiple roots. If it has, the problem stops at one blow up. If not, then we blow up the singular points corresponding to multiple roots. This is the blow up process in case of characteristic singular points. And this is the blow up process related to the Newton diagram is similar. If you have a non-degenerate Newton diagram, then the process stops and you calculate analogues of Lyapunov focus values. If the Newton diagram is degenerate, then after a blow up, you find some bad singular points and you repeat, you take Newton diagram for them and you repeat the process. And the process ends up in the final number of steps, except for the codimension infinity. And this process allows you to determine whether the point is Lyapunov stable or unstable. So this is the contribution, I should say the lifetime contribution of Natalia Medvedeva. So let me stop the mathematical part of my lecture here and say you a few words about first life in Moscow. About, I should say, 17 years ago, a new mathematical department began to work in Moscow, and it is a mathematical department of the Higher School of Economy. It is a child of the Independent University and the Higher School of Economy jointly, and this is the most popular mathematical department in Moscow now. Most strong mathematical school children go to this department rather than to the old classical Lomonosov University Mehmat department. Definitely the new department inherited best features of the old one, so it is a child of the old department too, but it is a child that has grown up more than his father. This department invites foreign master students and graduate students. Be aware of that. This is what I wanted to say first. And second, I wanted to say my cordial gratitude to all the people who organized this event. And the first for my dear student, Laura. I do not find Laura. Where are you? Yes, Laura, many cordial thanks. And thanks to everybody for your enthusiasm and persistence.
Thank you very much. Is there any question already?
For many decades, I've been told to avoid saddle connections, and now I learned that I have to work with it.
But they are in the neighborhood of the singular point, and before you blow up, there are no saddles, no connections, and so on. And after you blow up, you get quite a non-generic vector field, and saddle connections may occur there.
Whatever, what you told yesterday on the other days brings me to think that at my age I have to change my mind about saddle connections.
Well, when you, even in the simplest homogeneous case, when R is non-zero and has simple roots, you can see this picture. The pasted-in phase curve brings several singular points on it. If they are saddles, then unavoidably saddle connections occur.
Okay, but so I have to study saddle connections? I don't say I have to. I would like to understand saddle connections, but I think I would need some more references for this.
Well, I think that, yes, the textbook of Dumortier, Libre and Artes, may be a good reference. In my book with Yakovenko on analytic differential equations, the desingularization theorem is also proved, and some consequences are discussed. And the picture like this is a sort of exercise. You take, say, x dot equals to y cube, y dot equals to x cube, you blow up and look what happens.
Write some references for us. Not now, but at some point.
Mm-hmm.
I think will be useful for many people.
I do not write the title, Lectures in Analytic Differential Equations, Dumortier. And co-authors, Libre and Artes. I do not remember the exact title of the book. It is Qualitative Theory of Differential Equations.
Any other question?
Allow me to make a picture of the class. Thank you.
Professor, you make the result in the real analytic singular point in a neighborhood of the real plane.
Yes, yes.
What is the implication of this theorem when you consider the complexification of the vector field to C2?
Yes?
Since the power series is real, then some symmetry, respect to conjugation in CQ
Yes?
appears. Then what is the consequence of these results when you consider the complexification?
When you make a blow up in the complex domain, first of all, when we make a blow up in the real domain, you get a circle instead of a singular point. When you blow up in the complex domain, you get a Riemann sphere instead of the singular point. And on the Riemann sphere, there are singular points not seen from the real point of view. And for instance, this curve is homotopic to the product of these two loops, and you may describe the monodromy map along this real curve as a monodromy map along these two loops. So there is a complex approach to all this and the relation between the real and complex case, but not very direct consequences, not very direct relations. Okay?
Well, any other question? Well, I have a small one. In the middle of the blackboard, so you said it is with a slightly changed definition. It was solved. What was the changed definition? Is the analytically unsolvable?
Medvedeva changed the definition in the following way. In the old sense, the definition, the problem is analytically unsolvable. The new sense is the following. You may ask, what is the class of the vector fields with a given Newton diagram? For sure, there is an infinite number of diagrams and therefore an infinite number of classes. But you always may determine to what class your vector field belongs. Then there is a process of Newton diagram blows ups with the further Newton diagrams appearing. And the simple monodromy class in terms of Medvedeva is the set of vector fields with a given Newton diagram, with a given Newton diagram after the first blow up, and so on. And you can determine to which monodromy class a vector field belongs. Then you fix this monodromy class, and inside this monodromy class you solve the stability problem. And the sets of neutral jets are semi-analytic inside this set. So it is similar to the graph of the function sine 1 over x. This set is not semi-analytic, but it is analytic in the open half plane x greater than 0. And it is semi-analytic on the real line. So inside the simple monodromy classes, which are already distinguished and are like x greater than 0 in my simple example, the sets of neutral jets are analytic, semi-analytic. But if you consider several adjacent simple monodromy classes, then the neutral subsets approach the boundary of the class in a non-analytic way. And therefore, the problem is not analytically solvable in the traditional sense.
Thank you. More questions?
I have no questions. I just want to thank Professor Ilyashenko. He has gave us with his natural generosity, with care, with simplicity, with love to the students, to all the audience, and to mathematics, and we left us, as Jesus already said, a great legacy. Thank you. Thank you.
Thank you, Laura. Thank you all. Thank you. Thank you. Thank you. Thank you, Laura. Thank you personally very much. Thank you. Thank you.